This is video 5 of topic 10 on groundwater hydrology. In this video we'll talk about capture zone curves. The most common way to begin to clean up contaminated groundwater is through the installation of extraction wells. Such wells pump water from a contaminated aquifer, which lowers the water table in the vicinity of the well, creates a hydraulic gradient, and then draws the contaminant plume toward the well. You can see this here. If extraction wells are properly located, the polluted groundwater can be pumped out of an aquifer, cleaned in an above-ground treatment facility, and then used or returned to the aquifer. The above-ground component may look like this. The overall process is called pump and treat technology. Pump and treat systems remove contaminants through mechanical, chemical, and biological means, and they discharge water to the subsurface, surface, or potentially the municipal system. There are several important limitations. The first is that the effectiveness depends on the aquifer geology and the type of contaminant. The second is that the process is slow. It can take decades to potentially even centuries to remove the contaminated water, and yet this approach often fails to remove all of it. Thirdly, it is a very costly process. And finally, it does not always work, because some contaminants actually stick to the soil and rock, they're adsorbed, and they cannot be easily removed, desorbed. And so examples of this that we'll see in the next video, video 6, are non-aqueous phase liquids, or NAPLs. To capture a contaminant plume, we create a capture zone. In a region with a uniform and steady regional groundwater flow, streamlines are bent toward the well. The outer envelope of the streamlines that converge on the well are called the capture zone curve. And so here, the water that's inside the capture zone is extracted, while the water outside the zone is not. Note that the flow lines may curve towards the well even outside the capture zone, but the regional flow in the aquifer that's associated with the hydraulic gradient is strong enough to carry that groundwater past the well, and so it'll bend towards it but then continue past. Capture zone curves can be used as an aid to design extraction well fields for pump and treat systems. This is a concept from the work of Javendel and Sang from 1986. The capture zone analysis is based on an ideal aquifer, and an ideal aquifer has these characteristics. First of all, it's homogeneous, isotropic, it has a uniform cross-section, and it's infinitely wide. It can be either confined or unconfined. The drawdown is going to be insignificant relative to the total aquifer thickness, and the wells that are drilled extend downward through the entire aquifer thickness, and they extract uniformly from every layer. In all, these assumptions are not very realistic, really, but the resulting model gives considerable insight into the main factors that affect more complex models, and so it's useful to understand this overall approach. For a single extraction well at the origin of the coordinate system, right here, the following equation relates the x and y coordinates of the envelope that's surrounding the capture zone. And so it's y is equal to plus or minus q over 2bv minus q over 2 pi bv inverse tan or arctan of y over x. B is the aquifer thickness, v is the Darcy velocity or the conductivity times the gradient, q is the discharge or the pumping rate from the well, and then x and y are of course the coordinates. We can revise the equation in terms of the angle in radians from the origin to our xy coordinate of interest on the capture zone curve using this relationship. Tan of phi is equal to y over x, so that for 0 is less than or equal to phi is less than or equal to 2 pi. We have y is q over 2bv times 1 minus phi over pi. So this is our key equation here, actually. There are some important measures that we'll focus on in this course that result from this equation. As we get infinitely far away from that well, in other words, as we go farther and farther along the x-axis, phi approaches 0, so that y becomes q over 2bv. And the width of the capture zone, because y is just from the x-axis upwards, is actually 2y. Okay, so then if it's 2y, then it's q over bv. So the positive part is q over 2bv, and the total width of the capture zone is q over bv. Secondly, at x is equal to 0, or at the well itself, then phi is pi over 2, or 90 degrees, and then y is q over 4bv, which is half of this width, of course, and for 2y, the total width at the well is q over 2bv. There are some other important implications of the equation that we just saw. The first is that the width of the capture zone y is directly proportional to the pumping rate q. You can see it here. Y is directly proportional to q. Secondly, the width of the capture zone is inversely proportional to the product of the Darcy velocity v and the aquifer thickness b. And so this means that a higher regional flow velocity therefore needs a higher pumping rate to capture the same amount of plume. Further, there's usually some maximum pumping rate based on the acceptable drawdown at the well. So of course, as the discharge rate, Q, increases more and more, you're going to draw down more and more at the well. To use our capture zone curves for problem solving, we're first of all going to assume that the aquifer characteristics and the plume boundaries are known, and then we can use a capture zone type curve to draw the capture zone that corresponds to the maximum acceptable pumping rate. It'll look like this. So here's our capture zone, here's the location of the extraction well, and then here are the plume contour lines. And so we want that plume to be entirely contained within the capture zone. Here's the direction of regional flow, of course. So this will draw out the entire plume as it's drawn here. And so as I just said, we superimpose the plume onto the capture zone curve at the same scale to determine whether a single extraction well will suffice and where to place it. Our previous single well solutions are not necessarily the best, and the reason is the extraction well is going to be located very far down gradient from the plume. That means that a large volume of water has to be pumped before any of the contamination actually even reaches the well, and this could potentially be years of extra pumping time. That means, of course, much higher costs for aquifer rehabilitation than if we started extracting the contaminant almost right away. A better solution, then, would have more than one extraction well that are placed closer to the head of the plume. And so Javindal and Sang derived capture zone type curves for a series of n optimally placed wells. In this course, we'll most often see 2 wells or 3 wells that are optimally separated. Each of them pumps at the same rate Q, and all of the wells are going to be lined up along the same y-axis. What does it mean when we say the wells are to be optimally placed? We want maximum spacing such that no flow passes between the wells. In other words, a larger separation could result in some of that contaminant not being captured. It could flow right between the wells. And yet we want them far apart enough that we can have fewer wells rather than more. The optimal separation distance was found to be Q over pi BV. You can see it here for 2 wells and here for 3 wells. This optimal spacing means that 2 wells can capture a plume as wide as Q over BV and farther up gradient as wide as 2Q over BV. And then for the 3 well solution, we can capture a plume as wide as 3 over 2 QBV, and here 3Q over BV. The general equation that we use for the positive half, the plus y component, of the capture zone curve for n optimally spaced wells that are arranged symmetrically along the y-axis is y is equal to q over 2bv times n minus 1 over pi times the sum of these phi I. And phi I is the angle between the horizontal line through the ith well and a spot on the capture zone curve. Single and multiple extraction wells that are lined up in front of an advancing groundwater plume can intercept pollution. By combining the use of extraction wells and injection wells, we can also protect down-gradient groundwater uses, like drinking water wells. Extraction wells, as we already know, lower the water table or the piezometric surface for a confined aquifer and draw a plume to the wells. Injection wells, on the other hand, raise the water table and push the plume away. And if we're careful then in our design of the location and pumping rates of such wells, then we can manipulate the hydraulic gradient. This allows us to control and remove the groundwater plume in a process called hydrodynamic control. Finally, the extracted contaminated groundwater can be treated and re-injected, or it can be released into local surface waters. Here are a couple of examples of hydrodynamic control. Strategy A has an injection well that pushes the plume away from our production well, and an extraction well that pulls the plume away from the production well. Strategy B has an injection well that pushes the plume into the vicinity of the extraction well to remove the plume more quickly, because it's pushing the water in the same direction as the groundwater flow. The advantages of this approach are that the construction costs are relatively low, and it's always possible to add additional wells if necessary because, of course, the contaminant plume moves relatively slowly. Further, the environmental disturbance on the surface is minimal. However, the operation and maintenance costs can still be high for this type of system, and the wells have to be pumped for many years until this plume is removed. There are alternatives to hydrodynamic control then, and one of them is to surround the contaminant plume with a wall of impermeable material from the surface all the way down to an aquitard. Many such physical containment schemes are possible. All of them involve different materials and construction techniques. One common one is a slurry cutoff wall, which is a narrow trench about 1 to 2 meters wide that's dug around the plume down to the bedrock and then backfilled with relatively impermeable mixtures of soil and bentonite clay. The slurry wall then stops the plume from migrating off-site, and remediation measures can be applied to clean the aquifer. Another interesting example is the Fukushima nuclear disaster back in 2012, I believe. This is where radioactive cooling water after the tsunami was leaked into the groundwater, and so their proposed solution was to make something like a slurry cutoff wall, but instead it was going to be an ice dam. So they were going to inject water and freeze it, and then keep that ice wall maintained through cooling the ground. If you're interested in reading more about this, here's a URL. This ends video 5.